Hello everyone. I finally have a sufficient voice that doesn't hurt enough to keep me from making videos at this point in time. So we're going to do a video lecture and all that good stuff. Yeah. I'm also a couple octaves lower than usual, so yeah, I can finally hit those bass notes. Not really, because it hurts. So before we get into today's lecture, just a few accounting things. One, I will be posting stuff for the midterm on Wednesday. So basically, I'll give you some old midterms where you can practice the problems, all that good stuff. I won't post the solutions until Friday, just to give you an opportunity slash force you to go through and work on them a little bit, but I will give them to you before reading week, so you'll have that there. I'm planning on giving, I believe, 3 copies of different exams, so you'll have that to go with. Beyond that, recall our homework is due on Friday. You have everything to do that, or everything you need to do that. And today there will be office hours, not hosted by me, but hosted by one of your TAs, in particular Paul, for those of you who know Paul. And that will be in E7 4417 from 5 p.m. to 7 p.m. And that's also posted on Learn. Okay, so without further ado, and before my voice dies, let's get into the lecture. So today's lecture is on relations, which we've already seen before, but we're now going to start examining them in a lot more detail. So let's just jump on in. So recall definition of relation. You can read this, so I'm not going to read it out loud. Yep, there you go. So hopefully I had enough time. It's basically just a subset of this guy, right? And previously, we examined special types of relations that were useful for doing things. Functions, I mean, you can't do computer science without functions. Well, yeah, right? So it's kind of fundamental. Then we have injections, which allow us like part of what we need to define an inverse. Surjections, which gives us another part that we need to formally define an inverse. Then we talked about bijective functions and inverse functions and all that good stuff. Lots of things that you need there, right? The natural question is, are there other useful relations that just aren't functions? And the answer to that is yes. So our focus on relations will focus on binary relations. So again, binary relation means two. Binary means two. So we have the cross product of two sets here, A and B. Okay, so there are things you can do with other relations like trinary relations, etc. But for the purpose of this class, we're going to just focus on the binary ones, and we'll do a deep dive in kind of classifying binary relations in some classic ways, right? So here you can just think of binary relations subset of some collection of ordered points in two-dimensional space, right? If you have a bigger database set, then you would care about the generalizations of higher order relations, right? For instance, a database with, say, 10 different columns in it, that would have 10 of these little sets being cross-product with each other. Okay, so for relations from A to B, where A is the same thing as B, we again can just write A squared. Okay, so standard notation that we have before, but this new relation, or this new notation, instead of writing this, sometimes we're now going to allow ourselves to write this. Okay, you'll kind of see why. It turns out, just to spoil a little bit, the operations greater than, less than, equal to, greater than or equal to, subset, and equivalence, like all of these guys here, this, that, subset of, equivalence. When you write A is less than or equal to B, you write it as this, right? So this notation here is kind of hinting at these guys. Okay, so again, we're only going to talk about binary relations. So like with functions, we can define a lot of the same type of properties for relations. So here's the properties we're going to define. Okay, so given this relation, the domain, again, is just this set. Nothing's changed, right? The only difference is now we're not talking about necessarily a function, right? So the domain is all the x's that appear in one of the ordered pairs, okay? So before, something like this wouldn't be a function. Because when you plug in 0, you divide by 0, right? But this is now a relation, and the domain of this relation would be, in this case, equal to all real numbers other than 0. So just subtract off our 0 set. And those are set brackets. There you go. Okay. So that's the basic idea here. So you already know it, right? But now you actually have to compute the domain. Right? So generally when you're doing something in calculus and you say something's a function, like 1 over x function over the real numbers, and then like you're really treating it as kind of a relation for the purposes of that exercise, and then removing 0 from the domain when needed, right? Okay, yeah, and again, this will be always a subset of x. Before, the domain was always the set x, now it's just a subset of. Okay, now the codomain is y. Nothing there changes. The range is the exact same definition we had before, right? Again, the only thing that changed, instead of saying, well, f of x is equal to y here, I can say x is related to y, right? That's how to read this guy. Oh, and one other thing I should mention at this point, this is a Boolean value, right? Just how like 1 is less than or 2, that's true or false, right? Same thing here. X is related to y, or x is not related to y. Okay, next we have the image. Again, the image is going to be the same thing. It's just all the y's that I get by plugging in various values in for x. And we'll have some examples of these so on the next slide, so I'll kind of speed through these here. The next one we have is the inverse image or pre-image of a set. And what this is this is basically everything that maps to that set. So just like before, we get basically the exact same definition. We just change this up from what we've seen before. So hopefully these are familiar. But yeah, if you want, we have our little classic picture here where this is the domain. This is my codomain. Or sorry, no longer my domain. This is the set that I'm mapping from. This is the set that I'm mapping to. My domain now is going to be some subset here, right? That would be this guy. The codomain, again, is going to be this whole set here. Now let's suppose I have the relation where I have these two dots here and an extra dot here, and let's just throw in a few dots here. Okay, in this case, if this guy mapped here and this guy mapped here, and we'll say this term maps here, and this term maps here. Okay, so if we had something like this set over here, right, this bigger set is going to be our range. Our smaller set is going to be our range over here. The image of, well, if I asked the image for this single dot here, it would be these two dots here that this dot maps to. And if I asked for the inverse image of, say, the middle dot here, that would be just my whole domain because, hey, this dot maps to it, and yes, this dot maps to it. So same idea that we had before, right? Just some slight modifications. Okay, so yeah, again, we could also define injective, surjective. So in this case, this would be neither injective nor surjective, but we're not really going to do this. One, to not confuse you if I say, let this be injective, right? Because is it a relation? Is it a function? What type of thing does it have to be? It'll always be a function for this course. And two, we don't really need to do much with those injective and surjective relations because, again, the concepts are mostly meaningless if you don't have a function, right? The goal of having these is to get to invertibility. So yeah, like there are useful properties without having invertibility, but still, nevertheless. Okay. So yeah, and again, you can read the text there, but yeah. Okay, so let's go on to the next slide. Okay, so in this example, basically what we're doing is we're going to introduce you into relations by actually starting with a relation, right? So let G be the set of all the ordered pairs in R2 such that X is greater than Y. 1, prove this is a relation. You'll find that that's a very trivial task. Then find its domain, range, G of that set, and G inverse of this set. Okay, so to prove something's a relation, all you have to do is prove that it's a subset of some Cartesian product? So the answer is, look at it. Yeah, it's a subset. So if I ever ask you to prove it's a relation, there's nothing really to do there, unless you start with some weird exotic object, which, yeah, there's nothing to do. Okay, so now what is the domain of this? Well, to answer the domain, I need to know what all of the possible values of x's that are sitting in here, right? And that sometimes is non-trivial here, right? But if you look at this, I'm really just asking, like, what x's can I put here to be greater than some y? Well, if I pick y to be, say, minus x, this inequality is always true, right? And because this is true for any real number, I can plug any real number into here, right? So that tells me not just the domain, but also the range in this example. This tells me that the domain and range is all real numbers, because x can be anything. It has restrictions based on a particular y, but between all these ordered pairs, x can be anything and y can be anything, right? So, or can take on any values. So the domain of G is the real numbers, and the range of G is R. Okay, yeah. So hopefully that fits there. The next set is asking for the range, or sorry, G of 1, 2. So to find G of 1, 2, I need to ask, what are all the y's such that, well, 1 is greater than y, or 2 is greater than y, right? I want to figure out what all y's are related to these x's. Okay, so I need this or this to be true. So for this one, you can draw your, like, classic little number line. Okay, so if we draw the number line like you've seen back in middle school or whatever, so we have our 1 here and our 2 here. So we want all the y's that are less than 1. So we want this, or all the y's that are less than or equal to 2, or sorry, less than 2. So we draw this, and it's an or, so we want one condition or the other to be met. So if I put these two conditions together, this will give me all the y's that are going to be less than 2. Okay, so that's going to be my set there. So if we just chase this out, we get this. Okay, and generally, if you get more complex relations, you can't really draw these type of graphs. You'll really just have to think about what the relation means and break it down, right? For instance, subset is a relation. You'd have to do some set theory stuff there, right? So all the good things with sets that we did earlier on comes back again. Okay, so to find G inverse, we want to answer the question, what are all the x's such that x is related to 1 or x is related to 2? Okay, and here under this relation, we would get these two guys. So if I draw a number line, here I have my 1, here I have my 2, here I have x wants to be bigger than 1, wants to be bigger here. If I put these together, I get that ultimately this is going to have to be the case, right? So here we get this set. Or again, we know how to write these guys as intervals kind of thing. You can use the symbol infinity. Yeah, so you could do that alternative standard way of writing it. Okay, so note, this means that this operation in R2 is in fact a binary relation. So notice here, if I write 3, 4 is an element of G, I could rewrite this as 3G3, or 4 is greater than 3. Okay, now there's one kind of problem here with my definition of G as being the greater than operation, the greater than relation, because to define this, I used the greater than relation. So yeah, you generally want to avoid that. So how do we define this formally to avoid using this symbol to define itself? Well, here's the standard way to do it. So from the last slide, that's how we defined everything to be. Now we're going to formally define greater than without self-recurrence. And you might think for a while, like, what's the key idea of greater than? Well, the idea here is that x is strictly bigger than y, right? What does it mean for x to be bigger than y? Well, if I give you a number, say y, if I will, and I want to make it bigger, what I can do is I could say, hey, y is going to be smaller than y plus some small epsilon, where this epsilon is just anything that's in R plus, right? This would greater than would always be true in this case, right? So now what we'll say is, if you wanted to say that x is larger than y, we can take this idea and use ordered pairs, right? So basically, in ordered pair form, this would be y comma epsilon, y plus epsilon, comma y, right? So that's what we're going to do. Change our symbols around a little bit. We can now define G as this, right? So it's just the set of all ordered pairs, x plus epsilon comma x, where epsilon is some positive number. Okay, there we go. That does the trick, right? That's what it means to be greater than. Similarly, you can also define, say, less than or equal to, greater than or equal to, and ultimately we'll define equals later, because that's also a relation. Okay, so we can now say things like this, using this more convenient symbol, kind of in a formal statement now, right? Like we could formally define greater than. That said, we're not going to do too much with this definition. It's just mostly there for you to see where things actually come from, and to formally be able to define greater than, right? Like as I always say, it's either an axiom or it comes from something, and greater than existing isn't an axiom. It comes from this. Okay. Nevertheless, now here under this definition, if I really say something like 7 is greater than 4, what I'm saying is that there exists an epsilon such that this equality holds. So if you can't find an epsilon, the equality doesn't hold, or if you cannot find an epsilon such that the equality holds, then it's not true, right? Those things would not be related. Okay, let's look at another example. So here I'll just throw up all this. So basically what we're doing is we're going to do the exact same thing that we did before, but with the E relation, that is the equals relation. Okay, so just take a little bit of time, try this one on your own. I won't put a pause break, just pause the video, try this on your own. Okay, hopefully you've now tried it. So what's the domain? Well, the question is, what values in x can I plug in? Well, here we know that x comma x is always going to be an E for any real number x, right? So for all x in the real numbers. Okay, so we know this thing is true, right? And since this is true, I can plug in any real number for x, and it also gives me the range at the same time. So domain is R, the range is R. So now E1, we have to answer the question, what x's are related to 1, right? So, what y's are related to 1. So what y's in R do we have such that this is true? Well, in this case, under the standard way that we define equals and the real numbers, we know just 1, right? Further, to answer this question, we want to find the y's that are related to pi, or the x's that are related to pi's. So we want to answer this question, and of course, yeah, we know how to do that, right? This tells us that equals is also a binary relation. Now, formally, equals in R is generally just defined as all the ordered pairs of this form, right? Where x is in R, right? So that's generally how you would define this guy. Okay, and we're going to explore these two types of relation, these two examples actually are examples of particular types of relations that we will do a lot with starting next lecture, but then picking up once we get back in person. Okay, so you'll see a lot more of these. They're not going away. Just keep that in mind. Okay, so you can also do relations on more exotic sets. So for instance, let A be a set and let S be an element of the power set of A quantity squared. And we're going to let this S be this particular relation here. Okay, so let's break down what this is actually telling us. So I have a set A, right? And just to give you a concrete example here, A could just have, say, 1 in it, as an example. So the power set of A, right? This is going to be the set of all subsets of A, right? So this is going to be the null set and the set that contains 1. Okay. So now, if I want to take A squared, I want to take the Cartesian product of this, I would get ordered pairs. And in these ordered pairs, the elements are coming from here. So let's just write this out. I would have the ordered pair with the null set, comma, say the null set. I'll also have the null sets, comma, the set that contains 1. And I really wish this tablet had a higher resolution and didn't do that. And we'll have the null set still, or sorry, null set's done, right? We'll have the set that contains 1 with the null set. And finally, we'll have the set that contains 1 with the set that contains 1. Okay, so it's basically the things here are just ordered pairs of sets, right? Now, S has an extra restriction, right? It's basically saying it's going to be all the ordered pairs XY, where XY is our subsets of A, so they come from A, and X is a subset of Y. Okay, so this whole thing of S being a subset of the power set of A squared, why do we need that? Well, here, if these things are going to be subsets of A, right, that tells you that the element here has a data type, or it's coming from the power set of A, right? Because A, like to be a subset of A, you have to be an element of the power set. Same thing here for this Y, right? And then over here, with this X being a subset of Y, that's kind of the restriction that I want. So this part, if we clean this up a little bit, this part is basically telling you data type, right? Formally speaking, you can remove this since I had this information here. And this bit here is telling you the interesting bit, okay? So it's just basically saying that this is the subset relation. Okay, so what's its domain? What's its range? So the domain of S is just going to be A, right? Or the power set of A, right? So here, if you notice, if Y is all of A, which it's allowed to be, then in this case, I'd pick up all the subsets of A, which would give me the power set, okay? Now, the range is asking the question, what things can go in here for Y to have an ordered pair? Well, Y could be all the way up to A, and Y can also be all the way down to, quote unquote, the null set, right? So if you kind of put those two things together, we get Y is allowed to be anything you want it to be, as long as it's in the power set of A. So the range is also the power set. Okay, and again, this tells us that the subset operation is, again, one of these binary operations. Okay, so let's go on to the next slide real quick. So the following of these guys are special types of relations. And I've introduced these earlier in the class, just got, well, some of them. The null set is always going to be a relation, right? The null set's always a subset of A cross A. And that's just going to be called the empty relation or the null relation, okay? So here we have two ideas. We have the null set, which is just a set, right? And has kind of set algebra properties like the null set intersected any set is the null set, etc., right? But we also have the same symbol, but we can treat it as a relation, right? So as the empty relation, I can talk about relational properties of it. But really, this is just a way of telling the reader what our focus is. So if you still called this the null set all throughout, there's nothing wrong with that. This relation, where I have some arbitrary set A and just take all the ordered pairs A comma A, is called the equality or identity relation. It's the generalization of the idea of equals. Here, A could be the set of all matrices, right? So this is defining, say, matrix equality, if you will. A could be the set of all functions. So this would be defining function equality, which that gets a little messy because functions, you need to define equals in a very particular way, but you get the idea. Okay. This guy, if I take A squared, that obviously is a subset of A squared. It's called the universal relation. It's the biggest one you can pick. Everything's related to everyone. And finally, this last idea comes in handy for a couple various things. One is actually for computing inverses of functions. If R is a relation on A and B is a subset of A, then I can restrict that relation to this subset. Starting to lose my voice. Yeah, so this B or R restricted to B is just the intersection between these two sets. This thing is a relation on B. And what does this thing do? Well, really what we're doing is we're taking the set of ordered pairs that we had from R and removing all of the ordered pairs that don't have components that are also in B. So as kind of a picture, if I had, say, these 3 dots, if this is A and A, I could have maybe something like this, and I could, here, I could say, I don't want all of these dots, right? I don't want 2 copies of this set, these sets, if you will. I could say, hey, I want to restrict it to the things above here. And if you do that, you would remove this ordered pair, right? That's the idea. And we call this the restriction of R to B. Okay, and now here, if I have an injective function, recall if I have some function from A to B, and this thing's injective but not surjective, then what I could do is I could build F, right? And here for the purpose of this, let's just say A to A. So it's injective but not surjective. What you could do is you could build a new function F that's going to be restricted on B, and this is going to be from B to B, where B is going to be the range of F, right? So if you did this, this new function would be invertible, right? That's the kind of classic thing here. Or you can do the thing, if you want to be one more example, you can take your sine function. We know this function's not invertible, which is a problem because we want to invert it really badly. So what we do is we restrict our domain to this interval here, and on this interval it's bijective, therefore I can take an inverse, right? This is formally how you do that. Okay, so exercise, prove that all of these are relations. Well, that's pretty trivial, right? Just, are they subsets of A cross A? Yeah, so the non-trivial bit is kind of here, but again, it's pretty trivial, but try it nevertheless. Okay, so all of these guys are binary relations on Z, Q, R, and all subsets of these sets. So yeah, relations appear everywhere. They're really quite useful. So don't turn off the video if you made it this far. I'll introduce assigned reading, and then I'll actually talk a little bit about the assigned reading, because there's part of it that I want you to actually do, because it can come in handy. So there's the reading from the course notes, there's your Schwam's stuff. We've used this before. I'm just reusing the meme, low effort, yeah. Yeah, okay, so over here, they have these pictorial representations of relations. I do want you to actually know this. So honestly, read this section, right? Like, read this on your own. Basically, the idea is all this stuff that we've been doing with relations over here, you can actually graph these relations, right? So for instance, if I asked you, hey, what's the graph of the relation, this equation? When I say the relation, I mean the ordered pairs x comma y that satisfy this, right? Well, that's going to be the circle, right? Or you could have more complicated things, like say here, and let me get access to, there you go. So like here, I would say from this context that 4 is related to 1. Why? Because there's an arrow going from 4 to 1. 4 is also related to 3. And make that a better 3, then etc., right? Just follow the arrows forward. 2 is related to 2, right? So you can have these little graphs that represent a relation. And the reason why I want you to read this, it's a very short section, but the reason why I want you to read this and to kind of digest these ideas a little bit is that next lecture, and then a lot more next week, we'll talk about different types of relations. And some of those relations have nice graphical ways of thinking about them, which I will, for our purposes, represent as tables. You'll see when we get there. But if you have this idea in the back of your head, it can help you digest the material. Okay, so I made it through the lecture. My voice is completely shot and hurts a little bit, but nowhere near as bad as before. Yep, I wish all of you the best of luck with the various things. And again, this material that we covered today is not on the midterm. Maybe you should have started with that, but haha, I tricked you to watch the video. If that's the case. Anyways, I'll talk to you guys later.